In the previous video, we have discussed that in tensile test we will be applying some elongation and we will be measuring what is the load exerted on the specimen due to that elongation, and using that we will be drawing the stress strain curve, right? Now the question is, does the rate of applying elongation influence the stress strain curve? The quick answer is yes, it will influence. And what is its effect? That's what we are going to discuss under the topic effect of strain rate on flow properties. Okay, so if we say so look at this table. So this table has been given for different test conditions. Okay, what should be the strain rate we have to use? Okay, and what is the effect of strain rate? So that we can observe from this figure. So where x-axis is strain rate epsilon dot, and this y-axis is sigma naught, which is the yield strength. Okay, and if you see, I mean, both axes are in it's a log plot. Okay, now if you see the room temperature, so what we observe is if we keep on increasing the strain rate, okay, there is an influence, there is a little increase in the sigma naught. Okay, the yield strength is increasing if I increase the strain rate. Okay, but that isn't significant. But at the same time, at an elevated temperature, if the temperature is very large, like 870 Kelvin, now if you see, that influence is very large. Okay, the influence is very large in sigma naught. Okay, so at an elevated temperature, this strain rate effect is considerable. Okay, we can't omit that. Okay, so not only that, but if you see from these conditions, if it's going to be like a high speed testing or hypervelocity testing, they are having a particular strain rate, because these strain rate are going to influence the mechanical property. That's why they are having a particular standard of strain rate in order to do these testing. Okay, now so from this picture, from this graph, we could observe that there is an influence of strain rate. Okay, now before discussing about the relation between this strain rate effect, in order to write it in the form of equation, how are we going to maintain a particular strain rate? So that's the question we are going to discuss. Okay, so now E is the engineering strain, and E dot, so the engineering strain rate, okay, or conventional strain rate, E dot, so is equal to, so where E is equal to L minus L naught by L, and if I substitute in the place of E, finally I will get V by L naught, where V is the cross head velocity, L naught is the initial gauge length. Okay, so in order to maintain the conventional strain rate constant, okay, all I have to do is I have to maintain this V, the cross head velocity, to be constant. Okay, by doing that I could achieve E dot to be constant. But what if I require epsilon dot to be constant, where the true strain rate to be constant? Okay, at that time what is the condition? If we see epsilon dot, which is equal to d epsilon by dt, where epsilon is ln of L by L naught. Okay, if I use this relation and if I calculate what is epsilon dot, it will provide me V by L. okay, where if you see with respect to time, so if V is going to change, okay, L should also change in order to maintain this epsilon dot to be constant. Okay, so that is one thing we need to understand. So if I just keep my crosshead velocity constant, I am not having a constant strain rate. Okay, I'm just having constant conventional strain rate but not a true strain rate. Okay, so with respect to L, I have to adjust the V as well in order to keep this epsilon dot to be constant. Okay, now from this picture, the relation between sigma naught and the strain rate is given by this. Okay, that is easy to understand because in a log plot, okay, if you observe a straight line, then the relation between these two quantities will be in the form of power law. Okay, so therefore from that we could say empirical, this is an empirical relation, it's not a derived one or anything. We could say from that relation it's sigma is equal to some constant into epsilon dot to the power of m, where this m is known as strain rate sensitivity, which is nothing but the slope of that line. Okay, and it has a value, a constant value for a given epsilon and given temperature. Okay, so these values depends on C and M, or depends on the epsilon and T. Okay, so this is the general relation between flow stress, which by flow stress we mean the yield stress. Okay, and the relation between flow stress and strain rate at a particular strain and temperature. Okay, now let's see an example. So in this example, a pure aluminum has been considered, and it's been considered at a particular true strain value for a particular epsilon value. Okay, and for two different temperature, one is for 294 Kelvin. At that time the C value is this and M value is this, and for a different elevated temperature, these are the C and M values. Okay, now so what's been asked is, what is the influence of strain rate at this temperature and at this temperature when I increase the strain rate to the order of 2, okay, the order of magnitude to 2. Okay, so first let's assume that epsilon dot is 1. Okay, at that time what I observe is sigma, okay, is 70.3. so when I maintain epsilon dot to be 1, then my yield stress is 70.3. but at the same time, if I increase the strain rate to the order of 2, then in the place of 1 I put 100. Okay, at that time what I'm getting is 95.3. okay, so the ratio is 1.35. there is a slight increase in the yield strength, which we could understand quantitatively. Okay, so now at the same time, when I raise the temperature to 713 Kelvin, okay, now see what is the value we have got for sigma naught. So when epsilon dot is 1, then I am getting 14.5, and epsilon dot is 100, I am getting 38.3. so the ratio is 2.64, which is a lot considerable. So the yield strength value has got doubled actually due to the different strain rate. Okay, so the main influence is due to this factor. Okay, of course there is also an influence, but this is a very big influencer. Okay, So just by having what is the value of m, we can say what is the effect of strain rate for that material. Okay, so when we do the tensile test, we should also need to know what is the strain rate I am applying in order to get my stress strain curve. Okay, so that's all about this topic. Thank you.